There are two ways to put an app in its own box on one server, a container and a virtual machine. From the outside, they look identical. Your app runs, it is isolated, it cannot see the neighbors. Inside the machine, they are not close at all. One of them is about 50 megabytes and starts in half a second. The other is 2 gigabytes and takes half a minute. That gap is not sloppy engineering. It comes from one design decision, and today we are going all the way down to it.
Here are both of them, stacked from the metal up. At the bottom, the same physical server. Now watch the layer that decides everything, the kernel. The kernel is the part of an operating system that actually talks to the hardware, the disk, the network card, the memory. On the left, with containers, there is exactly one kernel, and every container shares it. On the right, every virtual machine boots a kernel of its own. One kernel or many. Everything else follows from that. So what is actually inside a container image? Let us read one. This is a Dockerfile, the recipe for the image. Line 1 picks a starting point, a slim Python userland. That word userland matters. It means the files and the programs an operating system ships without the kernel. Then we copy in our code, install our libraries, and say which command to run. That is the whole image, around 50 megabytes of files. Notice what is missing. Nothing in here boots an operating system.
Because nothing has to. The kernel is already running. It is the hosts. So when you start a container, you are not starting a machine. You are starting an ordinary process on that host. List the processes on the server, and there it is, with a normal process number sitting next to everything else. Then look from inside the container, and that same process calls itself number 1. Same process. 2 different numbers, depending on who is asking.
That renumbering is the whole trick, and you can do it by hand in one line. On the host, count the processes, 312. Now run unshare. Unshare asks the kernel for a new namespace, which is a private view of one kind of resource. Here we ask for a private view of process numbers. Count again from inside. 2. Nothing booted. No machine appeared. We made one system call, and the kernel simply changed what this process is allowed to see.
Containers are built out of that one idea, repeated. There is a namespace for process numbers, one for the file system, one for the network, one for the machine name, one for user identities. Each one hides a different slice of the machine. That covers what a container can see. What it is allowed to use is a second kernel feature, called control groups, or cgroups for short. Cgroups put a ceiling on processor time, on memory, and on how many processes you may start.
You have used them already without noticing. These 2 flags on Docker run, memory and CPUs, are cgroups. And you can read back exactly what Docker wrote on the host in a plain text file. Half a gigabyte of memory, 1.5 processor cores. If your app goes over that memory number, nothing inside the container reacts. The host kernel kills the process. The limits are not in the container. They live in the kernel underneath it.
Which brings us to what it costs. Every container on that server is trusted to the same single kernel. That kernel is the floor under all of them. If somebody finds a bug in it, the crack does not stop at one container. It runs under every container on the box and under the host itself. The second cost is quieter. One kernel means one kind of kernel. You cannot run a Windows kernel on a Linux host. And on a Mac or a Windows laptop, Docker quietly runs a hidden Linux virtual machine to make containers possible at all.
So here is the other answer, as a command. This starts a virtual machine. We give it 4 gigabytes of memory, 2 processor cores, and 1 disk file. That disk file is the whole difference. It is not application files. It is a complete computer's disk, a bootloader, a kernel image, a full operating system. When this command runs, that guest kernel boots from scratch, the same way a real machine does, which is exactly why it takes tens of seconds instead of half a second.
And this is what those seconds buy you. The software running the show here is called a hypervisor. It hands every guest a set of fake hardware, a virtual processor, virtual memory, a virtual disk. The guest kernel talks to that fake hardware, never to the real machine. So a crash or a break-in inside one guest hits that guest's own kernel and stops at the fake hardware.
It has no path into the host and no path into the guest next door. That is why cloud providers put different customers in different virtual machines. Now the arithmetic, because this trade is easier to see in numbers. Take one server with 64 gigabytes of memory. Containers at roughly 100 megabytes each, that is about 640 of them. Virtual machines at 2 gigabytes each, about 32. 20 times the density, on identical hardware. And that 20 is not magic. It is precisely the guest operating systems you did not boot. You bought it with a thinner wall.
Which is why the honest answer is not one or the other. Look at how a cloud actually runs your code. You rent an instance, and that instance is a virtual machine. It is the wall between you and other customers. Then inside it, you run containers, and those are the boxes between your own services. A hard boundary on the outside, cheap, fast boxes on the inside. The managed container platforms are that same arrangement, with the setup hidden from you.
So the whole thing in 4 lines. A container is a process that the host kernel isolates, using namespaces for what it can see and cgroups for what it can use. A virtual machine is a whole computer that a hypervisor fakes, running a kernel of its own. Containers buy you density and speed. Virtual machines buy you a hard wall and any operating system you like. And in production, you usually get both, stacked.
If that made the difference click, hit like and subscribe. One concept, all the way down to the code, every time. There is a 90-second version of this in the description if you ever want a short one. Next up, what Kubernetes actually adds on top of the container you just met.